So here I'm saying that iron 3 plus, and we observed firstly in this case so we said so we have observed, as I was saying, that okay, we got to know, we have already studied earlier also, that it is going from high temperature to lower temperature, and it is going from delocalization to the localized one. That is fine. Just a second. Okay. So this was completely delocalized, and both irons were coming as iron 2.5. How do we get to know? Its delta value is the average of iron 2 and iron 3. Now, earlier what we used to see that iron 2 plus was having major splitting compared to the iron 3, but here it's the reverse. And splitting of the iron 2 is very less. And we know that how and on what factor splitting depends. If I'll consider iron in plus 3 and iron in plus 2, low spin, firstly we will check this is an octahedral field. So iron 3 plus, how many d electrons are there?
5, ma'am.
So it is d5 low spin, and 2 plus would be d6 low spin. Now draw its energy profile. We will be having T2G, Eg, here energy, T2G and Eg. So d5 we have to fill as a pairing form because it's a low spin. So here it would be d6. So you tell me whether valence contribution is existing here, and what about the valence contribution here? Firstly, we will see whether lattice contribution is there or not. So these are two irons, and both are having sulfur, sulfur, and nitrogen, nitrogen bound system. So they are generally having this systems: sulfur, 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 nitrogen, nitrogen, nitrogen. So you tell me whether this system would be having lattice contribution or not, just looking at the lattice.
Ligands are same, ma'am. No lattice contribution.
Your point is valid, but the answer is wrong. Just see which ligands you are saying. I'm just talking about one set of atoms.
Okay, okay, ma'am. There are two types of ligand is available. Lattice contribution available.
Right. So when two types of ligands are present, then there can't be any symmetry. So therefore, no ligand lattice contribution is absent in both the cases. Because both the irons, we are saying they are having same kind of coordination, so not present. And similarly, lattice contribution is also not here, right? Oh, sorry, it is present. Sorry for that mistake. Because of the two different ligands, it is present. So it is present, and this is also present. Now, what about the valence contribution in D5 and D6?
Valency contribution available in D5, ma'am. Valency contribution not available in D6.
So what do you expect? Which is going to have more electric field gradient and delta EQ
value? D5 more electric field gradient.
Because both the parameters, when they both are there, in comparison to this one, only one parameter is there, another is not there. Therefore, it's delta EQ, or firstly we say electric field gradient, would be greater than the electric field gradient of Rn2 plus, and therefore delta EQ would be greater than this one. This is in case of Rn2 plus and Rn3 plus. And delta EQ is nothing but the separation between the two lines which has been splitted from one peak. So splitting would be more in case of Rn3 plus compared to Rn2 plus. That's why in this graph, we are having more splitting in the distance of the two peaks in Rn3 plus delta EQ compared to this delta EQ. It's very, very high. So delta EQ is very, very high than delta EQ dash. This is for Rn3 plus, this is for Rn2 plus. Now is this clear? This particular example?
Clear, ma'am.
Okay. Now we can shift to another set of example. We have example number 11, where we have already discussed in, I think, last to last session. We were having iron sulfur clusters. These are the electron transfer agents. There we have taken the example of rubidoxine. So this was rubidoxine. But now we are going to have a ferridoxine. In ferridoxine, we have two iron. That's why we are talking in mixed valence complexes. Here, both the irons are connected to this S16, and they are bridged by using sulfide ligands. So it is theoretically expected whenever we talk about the electron transfer agents, we talk about their oxidized and reduced state. So oxidized and reduced state. In oxidized, we are expecting both of them to be in Rn3 plus. And when I'm talking about reduced, so one electron transfer at one time. So one would go to Rn3 to Rn2. Clear up to this point?
Ma'am, once again explain, ma'am.
Okay. So we have considered the electron transfer agents where they have the ability to transfer the electron. So when something is transferring the electron, that means it is getting oxidized, right? So iron sulfur clusters, they are having iron as metal and they are bound with different kinds of sulfur. One is that bridging this sulfur, and this is your amino acid S16. So here, this is a mixed valence complex where two types, where iron is present, and we are calling it as an electron transfer agent. So firstly, we are expecting that since both of them, they are having similar kind of environment, same environment especially, so both iron is expected to be in Rn plus 3. And since it is a tetrahedral kind of symmetry, so the both would be high spin. There is no question of having in low spin, right? Tetrahedral mostly makes the high spin complexes. Now, when we are saying from reduced state Rn3 plus 2, electron transfer agents, matlab they can accept the electrons if they are in oxidized state, if they give the electrons if they are in reduced state. So this, when takes up one electron, so 3 goes to 2, so one Rn goes to plus 2. So it would be having two different kinds of iron. Here it is expected to have one kind of iron, right? But when it has been observed their delta values, in oxidized case, they were having 0.21 delta value. Here it was having 0.35 and 0.65. Okay. And when we have delta EQ, it is having 0.6 and this is having 0.6 and 2.7. Now, when we have considered the case iron in plus 3 and iron in plus 2, which one you have found to have more delta value?
Plus 3, ma'am. Fe plus 3.
But that is more negative, right?
Negative.
Right? So that is what it coming over here. This Rn3 is having 0.35 compared to the 0.65. This is less positive. That means more negative delta value. This is clear?
Clear, ma'am.
Right? And also we can see the splitting. Splitting is very, very high in case of Rn2 plus. So we will see the graph over here, the MOSFET spectra for this particular case. So what we are observing, this is a transmittance. This is velocity versus millimeter per second. Now, we are expecting in the oxidized form, there should be only one kind of peak because both are in iron 3+, right? And when we are saying that it is in iron +3 and +2, so iron +3 is moving to this side. And we have iron +2 as so iron +2 would be having so here is our delta value of iron +2, which is so this we have said it is 0.65 and the iron +3 value, it is your delta, which has been called as 0.35, right? Now, this is the case when both of them are in oxidized stage. That's why we saw only one kind of peak, and this is coming around 0.27. So I need to make it a bit there, that side. Here we are saying that it was in here. So slightly its value was 0.27. So this was a case when we were talking about the oxidized, where both the irons are in +3 oxidation state. And when we came to the reduced form, one was in +2 and one was in +3, and we can see that. Now the question was, why in case of iron in +2 is having more splitting and iron 3 is having less splitting? Now you tell me, iron in +3, iron in +2, we know that it is having D5 electrons, D6 electrons. Now, looking at this particular structure, what do you think, how the splitting will be? I'm just writing SNS, that is S cysteine only. So what do you think, how the splitting would be? So first tell me whether it is tetrahedral field or octahedral field. That means the ligands are making the coordination as a tetrahedral one or an octahedral one. Here, how many bonds are there?
Tetrahedral.
Okay. So this is tetrahedral field. So when we know the tetrahedral field, tetrahedral is not having symmetry. So that is Angirad. It is not having any symmetry. So their orbitals would be T2 and E. Whereas in case of octahedral, we know that it is having symmetry. So it becomes as T2G and EG. G stands for Girard, which stands for symmetry, having inversion center. That means if I'll start This is my metal. This is the ligand. This is having an octahedral. If I'll start with the center, I'll go up, I'll get ligand. I'll go down, get ligand. At the opposite sides with the equal distance, I'll be getting the same kind of ligand. So that is having a symmetry, that is having the inversion center. Whereas in case of the tetrahedral, if I'll start with, say, general tetrahedral would be like this way. If I'll go above, I'll get one, but on the downside, I won't be getting another ligand. So it is not having any symmetry, right? So these are the orbitals that we get from tetrahedral field. Now, in tetrahedral field, their energy levels are opposite compared to the octahedral, because in tetrahedral, whatsoever the T2 ligands are, T2 orbitals are there, dxy, dyz, dzx, they feel more repulsion, therefore their energy increased compared to in octahedral, whatever the axial are there. So these ligands, which are the axial ones, the dx square, y square, and dz square orbitals, which are along the axis, they feel more repulsion. That's why you might have seen the orbitals, right? We have dx square, y square. So this is the orbital diagram of dx square, y square, right? Positive and negative low. If I'm saying x and y, so here and z square would be along this direction. So when I'm saying like this way, that means they are along the axis. And in octahedral, ligands are along the axis. That's why the orbitals which are along the axis, they are in more contact with the ligand orbitals. And because of that, electrons in ligands, electrons in d orbitals, they feel more repulsion. Because of the more repulsion, their energy level increases. And Eg, we know that it comprises of dx square, y square, and dz square. And they will be having more energy compared to the T2G. And T2G comprises of dxy, dyz, and dzx. And they belong in between the axis. So if this is x and this is y, the loads would be long in between them. If this is y and z, and if this is the case of z and x. So you can see the orbitals, the lobes are in between the axes. So they don't feel, if my ligand, if I'm talking about the octahedral ligand, my ligand is here and the orbital of the metal, it is away from that one. So there won't be any repulsion. But in the case when I'm having here, it is along the axis and my ligand is also along the axis, there is too much of repulsion. So when repulsion is there, with the repulsion, energy increases. So that's why in case of the octahedral, EG are higher energy compared to the T2G. Whereas in case of the tetrahedral, our ligands, in tetrahedral field, ligands are in between the axis. Therefore, in between the axis, the metal orbitals which are there, they are dxy, dyz, dzx, that means T2. Therefore, in tetrahedral field, when we are talking about the splitting goes, E would be down and T2 would be above. Whereas in case of octahedral field, we have opposite, T2G would be there and EG would be above. Is this clear or should I need to explain it one more time?
Clear, ma'am. Clear.
Okay. So now, as I have said, that we have iron in 3 plus, iron in 2 plus, and since we got to know that it's tetrahedral field, now you tell me how the splitting will happen. So as I said, the above would be T2, and here it is E. Now tell me how the splitting is going to happen. Okay, for answering this, you need to know whether they are making high spin complexes or low spin complexes.
Ma'am, how it will be low spin or high spin determination?
In tetrahedral, generally it is only high spin complexes. So it does not pair because the energy gap for pairing that is very less in case of the tetrahedral. So no pairing occurs and therefore it makes the high spin complexes mostly. There are certain
Okay, ma'am. Okay.
really
Tetrahedral mostly high
high
spin
spin
complexes.
complexes. So we don't generally talk about the low spin complexes over here. So when we are saying that it is high spin, that means firstly we have to fill all the orbitals since it is D, so it would be D5 like this way. Here it is D6, so one electron would be extra. Now, as I have explained here, that splitting of the iron 2 is more compared to the splitting of iron 3. You can see directly from here. What is the factor that is responsible for more splitting? If I have a peak and peak has split it into two, so the distance of the two peaks would be this much or this large or very small. On what factor it depends. We have just seen the other cases also. So it's the electric field gradient, right? Whenever we talk about this
Electric, ma'am, electric field gradient is the reason for splitting of both Fe2 plus and Fe3 plus.
Right. So now you tell me which one is having more electric field gradient.
D6, ma'am, configuration.
Why?
More electric field gradient. Because the unsymmetry of electron distributions in E and T2 orbital.
Right. So it is having more electric field gradient. So is there any lattice contribution in both the cases? This is actual structure. This one. So are the two ligands that are connected to the iron are same?
Yes, ma'am. Yes, ma'am.
One is sulfide, another is sulfur cysteine. Are they same?
Both are different, ma'am.
So when both are different, both are giving lattice contribution. So electric field gradient is there, but in case of the iron 2, we have more. In case of the iron 2, we have more splitting compared to the iron 3. Clear?
Okay, ma'am.
Now we will take up another example of the same iron sulfur systems. So next we have taken the 4 iron 4 sulfur. Last time we had 3 iron and 4 sulfurs. So there we can have this tube type of so here would be iron. Alternatively, we are placing the iron. And there would be sulfur, 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 and sulfur. And these would be bound with S-cysteine, S-cysteine, completing its coordination, S-cysteine. Okay, so this is then 4 iron, 4 sulfur. Now there are a lot of questions regarding how this. Okay, before that we need to consider. Okay, we'll come to this later. So firstly, just a second. So earlier we had this rubridoxin. Sorry. So we had this ferridoxin, and in ferridoxin we had iron, which is bound with another iron, and S-cysteine, other one S-cysteine. This was ferridoxin, and we found that in oxidized state, it is existing as iron in +3, both the irons in +3, and in reduced state, it is in iron +3 and +2. And the values that we got for delta EQ and this isomeric shift for iron 3 was 0.6 and this was 0.27 and 0.6. This was for 0.35, 0.65, 0.6 and 2.7. This was for this case. But what if we replace these two with the N-histidine? So this is another kind of amino acid, N-histidine. So when we replace the iron, one set of ligands of the iron, so here it is now bound with N-histidine. This is N-histidine, which is having a structure of this and this one. So this is a neutral, whatever the amino acid will be there. This is a neutral amino acid, whereas cysteine, if we are having, that is sulfur bound with a negative charge. So this is negatively charged. So earlier we were having both irons in same coordination number, same coordination sites also. Both were having S-histidine. But now here we have replaced one set with the N-histidine, and therefore the name of this particular protein is risky protein. So the earlier one was ferredoxin. This is risky protein. And here, if you will see the oxidized form, here also iron in +3, both the irons in +3. So since they have different environments, now their delta value would be different. They can't be having one same value. So one is having 0.24, other one is having 0.32. Delta EQ value is 0.62, 0.91. Similarly, for the reduced state, they were anyway different. Iron 3, iron 2. So this would be having 0.31, 0.74, 0.63, 3.05. Now our main focus is in this one because the reduced state anyway was different. That is fine. But in case of the oxidized state, we said that their oxidation state is same, but still there are two delta values. That isomeric shift is different. Why? Because one side it is attached with S-histine and other side it is attached with N-histidine. So you saw that one is more negative or less positive compared to the other one. So this less positive one is belonging to this iron, which is bound with N-histidine, which is bound with, sorry, it's the reverse I'm saying. So this one is bound with, this stands for this iron S4, this particular case, this A1. And this more positive value stands for B, which is this one. Why? We have this N-histidine, which is a neutral ligand, and we have S-histine, which is a negatively charged ligand. So because of the more negative charged over there, it is shifting the isomeric shift towards the negative side compared to the which is having a neutral ligand. So that's why we have to be very careful when structure of this kind has been given, where the two irons, though it is in same oxidation state but bound with different ligands, we need to see and we need to assign which one isomeric shift value belonging to which iron. So you will be able to assign the more negative or less positive value goes to iron sulfur, because this is negatively charged ligand, which is increasing the negative value of it, or we can say that it is decreasing the shielding effect of the d electrons. So is this clear? They would be more accepting in nature compared to the N-histidine, which is just giving the lone pair storage. So it is behaving as a donor. That's why in case of N-histidine, it is having more positive delta value. Is this clear?
Clear, ma'am.
Okay. So now we are going to have the last example that I just draw the structure here. So I'll repeat it I'll make it over here. So this is a very important example because now here we will be having 4 iron, 4 sulfur. This is also electron transfer agent. So this kind of system is having a cube-like structure. Where we have iron, so alternate position we are having iron, and sulfurs are bridged in between. Okay, and this irons are connected to SST. Now, so there are two possibilities that have come for this particular system. First possibility and first class that we say, it is 4Fe, 4 sulfur pyridoxine. That means it is called as, in oxidized state, it would be +3, +3, +2, +2. So 2 irons are in +3, 2 irons are in +2, and reduced form, we know that one of the 3 oxidation gets to +2. So this is expected one. In this particular case, when we have these 2, 3 and 2 +2, why are we saying that it is 4Fe4 as pyridoxine? Because this requires -415 to -280 millivolt. The potential range for the redox potential range for this particular system, it's very negative. Why is it so? Because generally these kind of proteins, these kind of agents, they will be in hydrophobic environment, and that hydrophobic environment is not very suitable or favorable, we can say. So it is not favorable, unfavorable. Whenever we say that the system, whichever the surroundings in the systems are unfavorable, that tends to give you delta G value, that gives free energy value as positive. And when this is positive, the potential value E would be negative. So this potential is nothing but your redox potential, the capacity of going from one oxidation state to another. Redox properties, like one is getting reduced, other is getting raised. So that potential is in negative range. Whereas if you take the second possibility, which is called as high potential iron sulfur protein, short form is HIPIP. So they have a redox potential ranging from +90 to +460 millivolt, which is very high. Why is it so? This protein is also having same structure. Structure has not been changed, but only this is having a hydrophobic environment. Same it is having, but that hydrophobic environment is containing some protein molecules which are having amide chain, C double bond and H. Because of this is delta positive, this is delta negative because of their charge separation, and they balance out the charge. Whenever there is balancing of the charge, that brings favorability, and therefore delta G for favorable environment, it is negative, and corresponding to that, E value is positive. That's why your potential is positive. And in this particular case, HIPIP, high potential iron sulfur protein, the oxidized state, earlier case it was having 2 positive, 3 positive and 2 positive. Here there are 3 positives, 1 2 positive, and reduced state 3 3 2 and 2. So it's the opposite of what we were having in the ferredoxin cases. So now, how do we identify which one is what? So in case of this one, we are expecting that 2 are in Fe3, 2 are in Fe2 position. That means they should be having 1:1 intensity, right? So we are expecting it to have 1:1 intensity. But actually what happens in case of first case where we are having 4 iron, 4 sulfur, pyridoxine. In this particular case, I'm saying oxidized species are 2 iron, Rn plus 3, 2 iron, Rn plus 2. And in reduced state, 2 iron, 3 irons are like, so this will also be plus 2 because it is getting reduced. So it is plus 2. So now if you'll see here, it should be having iron in 3 plus, iron in 2 plus, both are 2:2, that is equals to 1:1, right? So we are expecting that there would be two kind of splittings and they both would be at same intensity. But actually, what we observed experimentally in the MOSFET spectra, we only see one kind of pattern. That means this kind of system only exists when it is having sorry 2.5 oxidation state. That means earlier we were expecting both iron 3 plus and iron 2 plus should be there, but it is having just iron 2.5. That's an average thing. That means it is a delocalized one and we cannot distinguish the two irons over there. So is this clear?
Okay, ma'am, clear.
So if now this is iron in 2 plus 2.5, iron 2.5, and all of them, that means all the 4 irons are in iron into 2.5. So when the reduction will happen, reduced state would be having 2.5, it's fine. And the other two will become iron in plus 2, iron in plus 2. So now this will give you a spectra where we will be having 4 peaks, 1:1 in density. So this would be having a ratio of 2.5 is to iron in plus 2. So this is what we are expecting. So this is opposite what we were expecting. We were expecting, okay, 3 in reduced state also. We were expecting it 3 irons would be in plus 2 oxidation state. So the intensity should be 3:1. But actually we got 1:1. That means earlier from the oxidized state, we got there are 5 irons which are having an average oxidation state of plus 2.5. And when that gets reduced, the 2 iron 2.5 turns to iron 2, and therefore we see 1:1 kind of spectra. Similarly, in case of HIPIP, that is high potential iron sulfur protein, here we have expected that oxidized is having 3 irons in plus 3 oxidation state and 1 is plus 2, and reduced state we had corresponding to this one. This becomes iron 2 and this becomes iron 2. But here also what we get, so here also, here we were expecting to have 3:1 intensity of iron 3 plus and iron 2 plus. But actually what we get, so iron 2.5 is to iron 2. That means 1:1 intensity. So here also 2 irons are existing as iron in 2.5 plus oxidation state, and other ones are existing as 3 oxidation state. Sorry. So it is not the case of iron 3 anymore. It is iron 3 and a combination of iron 2.5, and when it gets reduced, it will be giving you. So now we have iron 3 plus, iron 3 plus, iron 2.5, iron 2.5 plus, and when it gets reduced, it will be giving you iron 3 plus, iron 2 plus, iron 2 plus. So this is the way we can identify 2 different kinds of iron systems when we are having a mixed valence complex, and MOSFET spectra plays a very important role to identify that depending on the nature of